Hello there and welcome to the Sleepy Science channel. I'm so glad you found your way here tonight. Maybe you've had one of those long days where the world felt a little too loud, a little too fast, or maybe you're simply the kind of person who finds comfort in drifting off to sleep while contemplating the vast, quiet mysteries that stretch beyond our small blue planet. Either way, you're exactly where you need to be. Tonight, we're going to take a journey together, a slow, gentle voyage through the cosmic universe. We'll wander through star fields that have been burning for billions of years, float past planets wrapped in storms larger than Earth itself, and pause to consider the strange and beautiful architecture of space and time. There's something deeply soothing about the universe, isn't there? The way it makes our everyday worries seem smaller, lighter, almost weightless. Out there beyond the atmosphere, beyond the moon and the planets, the universe simply exists, patient, timeless, unhurried. You don't need to do anything special tonight. You don't need to remember facts or take notes. This isn't a test. This is just you, your pillow, and the gentle hum of cosmic wonder. Let your body sink a little deeper into your bed. Feel the weight of the blankets. Notice how your breathing has already begun to slow just a little, just enough. That's perfect. If you're new here, welcome. If you've been here before, welcome back. Either way, I invite you to subscribe if you haven't already and perhaps give this video a like. It helps others find their way to this quiet corner of the internet where sleep and science meet under starlight. But there's no pressure. Tonight is about letting go. So close your eyes if you'd like, or let them rest softly on a dim screen. We're going to explore the cosmos together, one gentle fact at a time, and by the end of this journey, I hope you'll find yourself drifting peacefully into sleep, cradled by the knowledge that you are part of something infinitely vast, infinitely beautiful, and infinitely calm. Let's begin. The universe began not with a bang and a loud sense, but with an expansion so smooth and silent that if you could have been there, though of course you couldn't, you would have heard nothing at all. Roughly 13.8 billion years ago, everything that exists now, every star, every atom in your body, every photon of light, was compressed into a space smaller than the period at the end of this sentence. Then it expanded, not into something because there was no something to expand into. Space itself unfurled like a gentle breath, and time began its patient tick forward. In those first fractions of a second, the universe was hotter than any star, glowing with pure energy. But it cooled. It always cools. And as it cooled, it became calmer, quieter, more like the dark velvet sky you might see tonight if you looked up through your window. That early universe was remarkably smooth, almost perfectly uniform, with only the tiniest ripples in density, variations so slight they were like whispers in an empty hall. Yet those whispers mattered. Over millions of years, gravity tugged at those tiny dense spots, pulling matter together slowly, patiently. Stars didn't form immediately. For a long stretch of time, the cosmos was dark, filled only with cooling hydrogen and helium drifting through the void. Astronomers call this the cosmic dark ages, and it lasted hundreds of millions of years. Imagine that, an entire universe holding its breath in the dark, waiting. There's something deeply restful about that image, isn't there? A universe taking its time, letting things unfold without rush. Eventually, the first stars ignited, tiny sparks scattered across the blackness, and the universe began to glow again, but gently, like embers in a dying fire slowly coming back to life. Stars are born inside clouds of gas and dust called nebulae, and these clouds are some of the most beautiful structures in the universe. They drift through space like cosmic veils, often glowing in soft hues of red, pink, and blue as nearby stars illuminate them. Inside these clouds, gravity pulls gas together into clumps, and those clumps grow denser and hotter. Eventually, if conditions are right, the core of a clump becomes so hot that hydrogen atoms begin to fuse into helium, releasing light and heat. A star is born. This process can take millions of years. There is no hurry in the cosmos. Everything happens in deep time on scales so vast that a human lifetime is like a single breath. And that's okay. You don't have to rush either. Not tonight. Not ever, really. The universe is teaching you that it's okay to take your time. Our sun is one of these stars, a perfectly ordinary middle-aged star that has been burning steadily for about 4.6 billion years and will continue to do so for another 5 billion or so. It sits in a quiet neighborhood of the Milky Way galaxy, about 2/3 of the way out from the galactic center, where things are calm and stable. Every second the sun converts about 600 million tons of hydrogen into helium, and in doing so it releases enough energy to keep our planet warm, to grow forests, to evaporate oceans into clouds, to power every heartbeat and every dream you've ever had. All of that just from fusion happening 93 million miles away. And yet the sun doesn't strain. It simply does what stars do, it shines. That's its nature, steady, reliable, calming in its constancy. The light you see from the sun actually started its journey at the core, but it didn't travel straight out. Photons, little packets of light, bounce around inside the sun for tens of thousands of years, zigzagging through the dense layers, colliding with atoms, changing direction again and again. It's a slow journey from the core to the surface, but once a photon finally breaks free, it races across space at 186,000 miles per second, reaching Earth in just over 8 minutes. So when you feel sunlight on your face, you're feeling the end of a journey that took millennia to begin. There's poetry in that. The light touching your skin is ancient and yet perpetually new, a gift from the cosmos delivered fresh every morning. And when the sun sets, it doesn't disappear. It simply shines on another part of the world, patient and endless in its giving. The moon, Earth's companion, is drifting away from us, but only very slowly, about 1.5 inches per year. Long ago, when the moon first formed from debris after a Mars-sized object collided with early Earth, it was much closer, perhaps only 15,000 miles away compared to the 240,000 miles that separate us now. Back then, the moon would have looked enormous in the sky, and the tides it caused would have been dramatic, towering walls of water surging across the young planet's surface. But time and gravity have a way of softening things. Over billions of years, the moon has gently spiraled outward, and as it did, Earth's rotation slowed. Days grew longer. The relationship between Earth and Moon is one of gradual change, of mutual influence, of two bodies dancing slowly apart but never truly separate. Someday, far in the future, the Moon will drift so far that total solar eclipses will no longer be possible. But that day is hundreds of millions of years away. For now, the Moon still hangs in our sky, familiar and comforting, a nightlight for the entire planet. The Milky Way galaxy, our home in the cosmos, is a barred spiral galaxy containing somewhere between 100 and 400 billion stars, though no one has counted them all, of course. From the side, it would look like a thin disk with a bright bulge in the middle, but from above, you'd see elegant spiral arms curling outward like a cosmic pinwheel frozen in a very slow spin. The entire galaxy rotates, but not like a solid disk. Different parts move at different speeds. Our Sun and Solar System orbit the galactic center once every 225 to 250 million years, a period sometimes called a galactic year. Humans have existed for only a tiny fraction of one galactic year. Dinosaurs lived and died within just a portion of another. And yet the galaxy continues its slow, patient rotation, unbothered by the rise and fall of species on one small planet orbiting one unremarkable star. There's comfort in that scale. Your worries, your stresses, your difficult day, they're all held within a universe that operates on timescales so vast that everything feels, in the gentlest way, temporary and okay. At the center of the Milky Way, there is a supermassive black hole called Sagittarius A, and it weighs about 4 million times the mass of our Sun. Despite that enormous mass, it's surprisingly quiet. It's not actively consuming vast amounts of material right now, so it doesn't blaze with energy like some black holes do. Instead, it sits there, calm and patient, a gravitational anchor around which the entire galaxy revolves. Black holes often sound frightening, but really, they're just regions of space where gravity is so strong that not even light can escape. They don't roam around gobbling up stars. They're stationary, predictable, and in their own way, quite peaceful. If you were far enough away, you could orbit a black hole just like you'd orbit a star. It would tug on you with gravity, but no more dramatically than any other massive object. The universe, even in its most extreme places, follows rules. There's order. There's rhythm. There's a kind of cosmic reliability that, when you think about it, feels almost like a lullaby. Between the stars, space is not completely empty. There's a thin mist of gas and dust, mostly hydrogen, spread throughout the galaxy. It's incredibly diffuse, far thinner than the best vacuum we can create on Earth. But it's there, filling the space between stars like a whisper fills a quiet room. This interstellar medium, as it's called, is where new stars are born and where old stars return their material when they die. It's a cycle. Stars form, burn, die, and scatter their ashes back into space, enriching the medium with heavier elements like carbon, oxygen, and iron, elements that weren't present when the universe was young. Those elements eventually become part of new stars, new planets, and yes, new life. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now, all of it was forged inside stars that lived and died long before the sun even existed. You are, quite literally, made of stardust. And that means you're part of the cycle too, part of the vast, slow, beautiful process by which the universe knows itself. Some stars, when they die, go out quietly. These are the smaller stars, like red dwarfs, which can burn for trillions of years, longer than the current age of the universe, before finally fading away. Others, the larger ones, die spectacularly in events called supernovae. When a massive star exhausts its nuclear fuel, its core collapses in a fraction of a second, and the outer layers explode outward in a blast so bright it can briefly outshine an entire galaxy. For a few weeks, A single dying star can be visible across millions of light years, and then it fades. What's left behind might be a neutron star, an object so dense that a teaspoon of its material would weigh as much as a mountain, or it might collapse further into a black hole. But even in death, stars give. The explosion scatters heavy elements across space, seeding future generations of stars and planets. Nothing in the universe is wasted. Everything is recycled, reborn, woven back into the tapestry. It's a reminder that endings are also beginnings, that rest is part of the cycle, that it's okay to let go. Light from distant stars takes time to reach us, and the farther away a star is, the longer its light has been traveling. When you look up at the night sky, you're not seeing the universe as it is now, you're seeing it as it was. The light from Proxima Centauri, the nearest star to our Sun, left that star about 4 years ago. The light from stars in the Andromeda Galaxy, our nearest large galactic neighbor, has been traveling for 2.5 million years. You are looking back in time, watching the universe's history unfold across the sky. Some of the stars you see may no longer exist. They may have already died, and we just haven't received the news yet. There's something gently melancholic and deeply beautiful about that. The universe is a storyteller, and the night sky is its archive, filled with light from the past, tales from distant places, messages written in photons that have crossed unimaginable distances just to reach your eyes tonight. Galaxies themselves are not static. They move, they collide, they merge. The Milky Way and Andromeda are currently on a collision course, drifting toward each other at about 70 miles per second. In about 4 billion years they will meet. But don't worry, galactic collisions are not violent in the way you might imagine. Stars are so far apart that even when two galaxies merge, individual stars almost never actually collide. Instead, the galaxies pass through each other like two clouds of fireflies mingling in the night. Over millions of years, gravity will pull them together into a new, larger galaxy, sometimes called Milkomeda. By then, Earth's fate will likely have been sealed by the aging sun, but the universe will continue, reshaping itself, creating new structures, new possibilities. Galaxies collide and are reborn. Stars die and are reborn. The cosmos is always in motion, always changing, and yet always somehow at peace with itself. The cosmic microwave background is the faint afterglow of the Big Bang, still detectable today as a dim, uniform radiation filling all of space. It's the oldest light in the universe, released about 380,000 years after the beginning, when the cosmos had finally cooled enough for atoms to form and light to travel freely. Before that moment, the universe was a hot, dense fog, opaque to light. But when atoms formed, the fog cleared, and light streamed out in all directions. That light has been traveling ever since, stretched and cooled by the expansion of the universe into microwaves. We can detect it with sensitive instruments, and when we do, we see a nearly perfect thermal glow at about 2.7 degrees above absolute zero, cold, ancient, and astonishingly uniform. It's like a cosmic baby picture, a snapshot of the universe in its infancy. And it's everywhere, all around you, passing through you right now, a gentle reminder that the universe has a history, a beginning, and a long, patient unfolding. Dark matter makes up about 85% of all the matter in the universe, yet we can't see it, touch it, or detect it directly. We know it's there because we can see its gravitational effects, the way galaxies rotate, the way galaxy clusters hold together, the way light bends around massive objects. Without dark matter, galaxies would fly apart. The visible stars and gas don't have enough mass to hold everything together, so there must be something else, something invisible, providing the gravitational glue. Scientists have proposed many candidates for what dark matter might be, exotic particles that barely interact with ordinary matter, but so far its true nature remains a mystery. And that's okay. The universe is allowed to have mysteries. In fact, the mysteries are part of what makes it so enchanting. Dark matter reminds us that there is more to reality than meets the eye, that the cosmos operates on levels we're only beginning to understand. It's humbling, yes, but also strangely comforting. We don't have to know everything. We're allowed to wonder. Then there's dark energy, even stranger than dark matter. It makes up about 68% of the total energy content of the universe, and it's driving the accelerated expansion of space itself. For most of cosmic history, the expansion of the universe was slowing down, held back by the gravitational pull of all the matter within it. But about 5 or 6 billion years ago, something changed. The expansion began to speed up as if some unseen force were pushing galaxies apart. We call that force dark energy, though we don't really know what it is. It might be a property of space itself, an intrinsic energy woven into the fabric of the vacuum, or it might be something else entirely. What we do know is that it's gentle, patient, and persistent, stretching space little by little, year by year. In the far future, trillions of years from now, dark energy may spread galaxies so far apart that the night sky will be mostly empty, each galaxy an island, alone in the dark. But that's unimaginably far away. For now, galaxies still cluster together, stars still shine, and the universe still feels full of light. The speed of light is a cosmic speed limit. Nothing with mass can reach it, let alone exceed it. Light travels at about 186,282 miles per second in a vacuum, and this speed isn't just fast, it's fundamental. It's woven into the structure of space and time itself. According to Einstein's theory of relativity, as you approach the speed of light, time slows down for you relative to the rest of the universe. If you could somehow travel at nearly the speed of light, and then return, you'd find that much more time had passed for everyone else than for you. This isn't science fiction. It's real physics confirmed by experiments. Time is not absolute. It bends, stretches, and flows differently depending on how fast you're moving or how deep you are in a gravitational field. The universe is far stranger and more flexible than our everyday experience suggests. Yet despite all that strangeness, there's a deep order to it. The rules don't change. Light always moves at the same speed, time always dilates in predictable ways, and gravity always curves space. The cosmos is consistent, reliable, a clockwork of immense scale and beauty. Space itself is expanding, carrying galaxies along with it like raisins in rising bread dough. It's not that galaxies are flying through space away from each other. It's that the space between them is growing. This expansion was discovered in the 1920s by Edwin Hubble, who noticed that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This relationship, now called Hubble's law, was one of the first major clues that the universe had a beginning and has been expanding ever since. But here's the beautiful part. There's no center to this expansion. Every point in space sees every other point moving away. If you were in a distant galaxy looking back at us, you'd see the Milky Way receding, just as we see that galaxy receding. Everyone is moving apart, and yet no one is at the center. It's a kind of cosmic democracy, a reminder that no place in the universe is special, or perhaps, that every place is equally special. You are at the center of your own observable universe, and so is everyone else. Neutron stars are among the strangest objects in the cosmos. Formed from the collapsed cores of massive stars after they go supernova, these stars pack about 1.4 times the mass of the Sun into a sphere only about 12 miles across. They're so dense that a sugar cube-sized chunk of neutron star material would weigh as much as all of humanity combined. Their surfaces are unimaginably smooth and hot, and their magnetic fields are trillions of times stronger than Earth's. Some neutron stars spin rapidly, hundreds of times per second, emitting beams of radiation from their magnetic poles. If those beams sweep past Earth, we detect them as regular pulses, like a cosmic lighthouse. We call these pulsars, and they're so precise that scientists have used them as natural clocks, stable to within microseconds over years. In a universe full of chaos and change, pulsars are little beacons of regularity, spinning in the dark, keeping time, reminding us that even in the aftermath of violent death, there can be order, rhythm, and a strange kind of peace. You're doing wonderfully. There's no need to hold on to any of these facts tightly. Let them drift through your mind like clouds across a summer sky. Notice your breathing, slow, steady, easy. Feel the weight of your body against the mattress. You're safe. You're warm. The universe is vast, but you don't have to carry it. It carries you. Let your shoulders drop. Soften your jaw. The cosmos has been unfolding for billions of years, and it will continue long after tonight. Right now, all you have to do is rest. Planets beyond our solar system, exoplanets, are everywhere. Since the first confirmed detection in the 1990s, astronomers have discovered thousands of them, orbiting stars both near and far. Some are gas giants like Jupiter, others are rocky like Earth, and some are in that tantalizing, habitable zone where liquid water might exist on their surface. We've found planets orbiting binary stars, planets that orbit so close to their suns that their surfaces are molten, and planets that drift through the galaxy without any star at all, rogue and solitary. Each discovery reminds us that planetary systems are not rare or special. They're common, perhaps even the rule rather than the exception. The Milky Way might contain hundreds of billions of planets. Think of that. Hundreds of billions of worlds, each with its own geology, its own weather, its own story. And we've barely begun to explore them. The universe is more crowded, more diverse, and more full of possibility than we ever imagined. It's a comforting thought in a way. We are not alone in having a world. Worlds are everywhere. One of the most famous exoplanets is Proxima Centauri b, a rocky world orbiting the nearest star to our Sun. It's only about 4 light-years away, practically next door in cosmic terms, and it orbits within its star's habitable zone. Of course, habitable doesn't mean it's a paradise. Proxima Centauri is a red dwarf star, small and cool, but also prone to intense flares that could bathe the planet in radiation. Still, the possibility exists. There might be liquid water, there might be an atmosphere, there might be something unexpected and wonderful. We don't know yet. Our instruments aren't quite powerful enough to see those details from here. But someday, perhaps, we'll know. And even if Proxima b turns out to be barren, there are so many other worlds out there. So many chances. The universe is patient, and so are we, slowly building the tools to answer the oldest question. Are we alone? But whether the answer is yes or no, both are profound. Both are beautiful. Saturn, the ring jewel of our solar system, is a planet that inspires calm just by looking at it. Those rings, made of countless particles of ice and rock, range in size from tiny grains to house-sized boulders, all orbiting in a thin, elegant plane. The rings are surprisingly delicate, in some places, only about 30 feet thick, even though they stretch hundreds of thousands of miles across. They shimmer and shift, influenced by Saturn's moons, which shepherd the ring particles into intricate patterns and gaps. The rings won't last forever. Slowly, they're spiraling inward, raining down onto Saturn's atmosphere. In perhaps 100 million years, they'll be gone, and Saturn will be just another gas giant, beautiful but unadorned. But for now, they're here, a fleeting masterpiece on a cosmic timescale, a reminder that beauty doesn't have to be eternal to be meaningful. Some things are lovely precisely because they're temporary. Jupiter, the giant of our solar system, is more than twice as massive as all the other planets combined. It's a world of storms and swirling clouds, with wind speeds that can exceed 400 miles per hour. Its most famous feature, the Great Red Spot, is a storm larger than Earth that has been raging for at least 350 years, possibly much longer. And yet, despite its size and violence, there's something oddly calming about Jupiter. Maybe it's the slow, stately way it rotates, completing a day in just under 10 hours. Or maybe it's the realization that this giant, chaotic world has been doing its thing for billions of years, utterly indifferent to the small dramas playing out on Earth. Jupiter doesn't care about your deadline, your argument, your restless night. It just spins, storms, and exists, a massive presence in the solar system, quietly pulling on asteroids and comets, acting as a kind of cosmic shield for the inner planets. In its own way, Jupiter is looking out for us, and it doesn't even know we're here. Mars, the red planet, is a world of dust and silence. Its surface is a cold desert, sculpted by ancient rivers and winds that still blow today, though the air is thin and the water is long gone, locked in ice caps or hidden underground. Mars once had a thicker atmosphere and liquid water on its surface, but it lost most of that over billions of years, slowly becoming the quiet, rusty world we see now. Rovers crawl across its surface, sending back pictures of rocks and dunes and distant mountains, and in those images there's a strange kind of peace. Mars is a world where nothing much happens anymore. The storms come and go, the dust settles, and the planet waits. There's talk of humans going there one day, bringing noise and activity and life. But for now, Mars is still. It's a place where you could imagine standing on a hill at sunset, watching the small, distant sun dip below the horizon, and feeling very far away from everything. And sometimes, far away is exactly where we need to be. Venus, Earth's twin in size, is a world of extremes. Its surface is hot enough to melt lead. Its atmosphere is thick with carbon dioxide and sulfuric acid clouds, and the pressure at ground level is equivalent to being 3,000 feet underwater. It's a hellish place by human standards, and yet, high in its atmosphere about 30 miles up, conditions are surprisingly mild. The temperature is comfortable, the pressure is like Earth's surface, and some scientists speculate that life, perhaps microbes floating in the cloud layers, could exist there. Venus reminds us that habitability is more complex than we thought. Life, if it exists elsewhere, might not look or live the way we expect. It might thrive in places we'd consider hostile, finding niches and possibilities we can't yet imagine. The universe is full of surprises, and Venus, despite its harshness, holds a strange kind of hope. Even in the most unlikely places, there might be room for life, for persistence, for something remarkable. Moons in our solar system come in astonishing variety. Europa, one of Jupiter's moons, is covered in a thick layer of ice, beneath which is believed to be a global ocean of liquid water, more water than all of Earth's oceans combined. The ice cracks and shifts, forming strange ridges and chaotic terrain, suggesting that the ocean below is active, warmed by tidal forces as Jupiter's gravity kneads Europa's interior. Where there's liquid water and energy, there might be life. We don't know. But the possibility is tantalizing. Enceladus, a small moon of Saturn, is similar. It shoots geysers of water vapor and ice particles into space from cracks near its south pole, material that comes from a subsurface ocean. Spacecraft have flown through those plumes, tasting the water and found organic molecules. Again, not proof of life, but ingredients. The universe seems to have scattered the building blocks of life generously across the solar system. Whether life took hold is still a mystery, but the stage was set over and over, in ways we're only beginning to appreciate. Titan, Saturn's largest moon, is the only moon in the solar system with a thick atmosphere, and it's one of the most Earth-like worlds we know, though Earth-like is relative. Titan's surface is cold, around -290 degrees Fahrenheit, and its lakes and rivers are made of liquid methane and ethane, not water. But it has weather, clouds, rain, seasons. It has dunes and mountains. It has a hydrological cycle, just with different chemistry. Standing on Titan, you'd see a hazy orange sky, and if you waited long enough, you might see methane rain falling slowly in the low gravity. It's a strange, alien version of Earth, a reminder that the principles that shape our world, atmosphere, liquid cycles, erosion, can operate under wildly different conditions. Titan is a world unto itself, calm and mysterious, waiting beneath its thick clouds. One day, we might send a drone to fly through that orange sky, skimming over hydrocarbon seas, exploring a landscape unlike any we've known. The asteroid belt, located between Mars and Jupiter, is often depicted as a dense field of tumbling rocks, but in reality, it's mostly empty space. The asteroids are spread so far apart that if you were standing on one, you'd be hard-pressed to see another with the naked eye. These rocky remnants are leftovers from the early solar system, material that never coalesced into a planet, likely because Jupiter's gravity stirred things up too much. Each asteroid is a small, irregular world, some just a few feet across, others hundreds of miles wide. They tumble slowly through space, silent and patient, witnesses to the solar system's formation 4.6 billion years ago. Some are rich in metals, others in water ice. Their resources, archives, time capsules. And they're no threat to us. Despite what movies suggest, space is so vast that collisions are rare. The asteroid belt is a quiet place, a graveyard that's also a nursery, holding the raw materials for future worlds. Comets are travelers from the outer reaches of the solar system, icy bodies that spend most of their time in distant, cold orbits far beyond the planets. Occasionally, gravitational nudges send them falling inward toward the sun, and as they approach, the sun's heat vaporizes their ice, creating glowing tails of gas and dust that can stretch for millions of miles. From Earth, comets appear as visitors, rare and beautiful, hanging in the sky for weeks before retreating back into the dark. Ancient people saw them as omens, but really, they're just messengers from the frontier of the solar system, bringing with them pristine ice and organic molecules from the early days of planetary formation. Some scientists think comets might have delivered water and the building blocks of life to Earth billions of years ago, seeding our oceans and eventually us. If that's true, then every glass of water you drink contains molecules that once traveled through the frozen dark, far from the sun, before arriving here. You are drinking comet water. You are made of the cosmos in the most literal sense. The Kuiper Belt and the Oort Cloud are vast regions of icy bodies surrounding the solar system, extending far beyond Neptune's orbit. The Kuiper Belt is a disc-shaped region where objects like Pluto reside, small worlds of rock and ice, quietly orbiting in the outer dark. Beyond that, much farther out, is the Oort Cloud, a spherical shell of icy nuclei that may extend halfway to the nearest star. It's the source of long-period comets, and it's so distant and diffuse that we've never actually seen it directly. We only infer its existence from the comets that occasionally fall inward. The Oort Cloud marks the edge of the Sun's gravitational influence, the boundary of our solar system. Beyond it is interstellar space, the vast emptiness between stars. And yet, even that emptiness isn't truly empty. There's gas, dust, magnetic fields, cosmic rays, thin and tenuous but real. The universe doesn't do true nothingness. Wherever you look, there's something, even if it's just a whisper. The sun will not shine forever, but its end is so far in the future that it feels almost abstract. In about 5 billion years, the sun will exhaust the hydrogen in its core and begin fusing helium. It will swell into a red giant, expanding outward until it engulfs Mercury and Venus, and possibly Earth. Our oceans will boil away, our atmosphere will be stripped, and the planet will become a charred, lifeless rock, or perhaps be swallowed entirely. But even this is not violent, not in the sense of sudden destruction. It will take millions of years. The sun will expand slowly, gently, like a long exhale. Eventually, it will shed its outer layers into space, creating a beautiful planetary nebula, and the core will collapse into a white dwarf, a dense, cooling ember about the size of Earth. And it will sit there, radiating its remaining heat into space for trillions of years, fading so slowly that the word fade almost doesn't capture it. The sun's death will be a slow, peaceful transformation, a return to quietness after billions of years of steady shining. White dwarfs, the remnants of stars like our sun, are incredibly dense objects. A teaspoon of white dwarf material would weigh about 15 tons on Earth. These stellar cores have exhausted their nuclear fuel and are held up not by fusion, but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too closely together. White dwarfs don't produce new energy. They simply radiate away the heat they have left over from their former lives as stars. Over tens of billions of years, far longer than the current age of the universe, they will cool and fade, eventually becoming black dwarfs, cold and dark, invisible except for their gravitational pull. But that future is so distant it's almost meaningless. For now, white dwarfs glow softly in the cosmos, embers of dead stars, still warm, still luminous, taking their time to say goodbye to the light. There's something poignant about that, a star that no longer burns, yet still shines. Binary star systems are common in the universe. In fact, most stars are not solitary like our Sun. They have companions, orbiting each other in a gravitational dance that can last billions of years. Some binaries are close, whipping around each other in hours or days. Others are wide, taking centuries to complete a single orbit. If you lived on a planet in a binary system, you might have two suns in the sky, rising and setting at different times, casting double shadows. The dynamics of such systems can be complex, and the presence of a companion star affects everything: stellar evolution, planetary formation, even the possibility of life. Yet despite the complexity, binary stars are stable, predictable. They follow the same gravitational rules as everything else. Orbits can be calculated, eclipses predicted. Even in pairs, stars obey the quiet mathematics of the cosmos, moving through space in harmony, bound together by invisible forces, partners in the long, slow dance of time. Star clusters are groupings of stars born from the same cloud of gas and dust, bound together by gravity. Open clusters like the Pleiades contain a few hundred to a few thousand young, hot stars, and they're loosely bound, destined to drift apart over millions of years. Globular clusters, on the other hand, are tight spheres of hundreds of thousands of ancient stars, some of the oldest objects in the galaxy, dating back to its earliest days. These clusters orbit the galactic core like satellites, dense swarms of suns so tightly packed that in their centers, stars can be just light weeks apart, far closer than stars in our neighborhood. If you lived near the center of a globular cluster, your night sky would be ablaze with stars, so many and so bright that true darkness might never fall. And yet, even there, most of space would still be empty. Stars, for all their brilliance, are tiny compared to the distances between them. The universe is mostly space, mostly silence, and that silence is part of what makes the light so precious. Red dwarf stars are the most common type of star in the universe, making up about 70% of all stars. They're small, cool, and incredibly long-lived. A red dwarf can burn for trillions of years, far longer than the universe has existed so far. Because they burn so slowly and efficiently, they're in no hurry to die. In fact, not a single red dwarf that has ever formed has yet reached the end of its life. They're all still in their first act, slowly fusing hydrogen, putting out a dim, steady glow. Planets can orbit red dwarfs, and some of those planets might be habitable, though they'd need to orbit close to the star to stay warm, and they'd face challenges like tidal locking and stellar flares. Still, red dwarfs are so common and so long-lived that they represent countless opportunities for planets, for chemistry, for life. If life is out there, much of it might exist under the light of a red dwarf, in a system vastly different from our own, yet governed by the same patient laws of physics and time. Brown dwarfs are sometimes called failed stars. They form like stars from collapsing clouds of gas, but they never quite accumulate enough mass to ignite hydrogen fusion in their cores. They're too big to be planets. Some are dozens of times the mass of Jupiter, but too small to be stars. They glow faintly from the heat of their formation, slowly cooling over billions of years. They occupy a strange middle ground, a twilight category neither here nor there. And yet they exist, drifting through the galaxy, dim and solitary, evidence that the universe doesn't always follow neat categories. Not everything becomes a star. Not everything ignites. And that's okay. Brown dwarfs are what they are, and they endure in their quiet way, reminding us that success and failure are human concepts. The universe just is. It doesn't judge. It simply allows all possibilities, bright and dim, to exist side by side. The life cycle of a star depends almost entirely on its mass. Massive stars live fast and die young, burning through their fuel in just a few million years before exploding as supernovae. Medium stars like the Sun live for billions of years and die gently, puffing off their outer layers and leaving behind white dwarfs. Small stars, the red dwarfs, live for trillions of years and may eventually fade so slowly we can't yet predict exactly how it will happen. There's an inverse relationship. The more massive a star, the shorter its life. It's almost poetic. The brightest stars burn out quickly. The dim ones endure. There's no best way to be a star. Each type plays its role. Massive stars produce the heavy elements needed for planets and life. Sun-like stars provide stable environments. Red dwarfs offer longevity. The universe needs all of them, and in their diversity there's a kind of balance, a completeness. Everything has its place, its time, its contribution to the whole. When stars explode as supernovae, they don't just scatter material, they create elements. During the explosion, temperatures and pressures become so extreme that nuclei smash together, forming elements heavier than iron, things like gold, platinum, uranium. Every atom of gold in every ring, every coin, every circuit board on Earth was forged in a supernova explosion billions of years ago, then scattered into space, incorporated into the cloud that would eventually form our solar system. You're wearing stellar explosions on your finger, carrying them in your pocket. The universe is extravagant with beauty and violence, and from that violence comes treasure. There's something humbling about that. The processes that create precious metals are the same that destroy stars. Creation and destruction are not opposites in the cosmos. They're partners, two sides of the same transformation. And in that transformation, new possibilities are born, new worlds. New chances for complexity, for chemistry, for life. The universe is constantly reinventing itself, and you are part of that unfolding story. Gamma ray bursts are the most energetic events in the universe. They occur when a massive star collapses into a black hole or when two neutron stars collide, and for a few seconds to a few minutes, they release more energy than the sun will emit in its entire lifetime. The gamma rays are beamed in narrow jets, and if one of those jets happens to point toward Earth, we detect it as a burst. They come from distant galaxies, billions of light years away, and even from that distance, they're stunningly bright. Fortunately, they're rare and far away, and they don't last long. If one occurred nearby, it could be catastrophic, stripping away the ozone layer and flooding the planet with radiation. But the odds are vanishingly small. Space is vast, and we are, in that vastness, safe and small. Gamma ray bursts are a reminder that the universe operates on scales of energy and violence we can barely comprehend, but also that those events are far away, contained. No threat to you tonight as you lie here, warm and quiet, beneath a sky that for us is gentle. Gravitational waves are ripples in space-time, caused by accelerating masses, usually massive, violent events like colliding black holes or neutron stars. Einstein predicted them a century ago, but they weren't directly detected until 2015, when instruments called LIGO picked up the faint vibrations from two black holes spiraling into each other over 1 billion light-years away. The signal lasted only a fraction of a second, a tiny warble in spacetime, but it was real. Since then, we've detected dozens more. Each detection is like listening to the universe, hearing events that produce no light, only gravitational whispers. It's a new way of observing the cosmos, and it's revealing things we could never see with telescopes. The universe is not just something we look at, it's something we can listen to. And what we hear is mostly silence, punctuated by rare, distant collisions, the echoes of events so powerful they shake the very fabric of reality. But here now, space-time is smooth and calm, undisturbed, cradling you gently. Quasars are among the brightest objects in the universe. They're powered by supermassive black holes at the centers of distant galaxies, actively feeding on surrounding gas and dust. As material spirals into the black hole, it heats up to millions of degrees, emitting enormous amounts of light, so much that a single quasar can outshine an entire galaxy of stars. Quasars were far more common in the early universe, when galaxies were younger and more chaotic, with plenty of material funneling into their central black holes. Today, they're rarer. Most supermassive black holes, like the one in the Milky Way, are quiet, dormant, having consumed most of the nearby material. Quasars are a glimpse into the universe's more turbulent youth, a reminder that the cosmos had an adolescence, a period of activity and growth. Now, in its middle age, the universe is calmer, more settled. Galaxies drift, stars burn steadily, and black holes wait. There's a rhythm to cosmic history, bursts of energy followed by long periods of quiet. Rest is built into the structure of everything. The observable universe has a boundary, not because space ends, but because light has only had a finite amount of time to reach us. The Big Bang happened 13.8 billion years ago, so we can only see objects whose light has had time to travel to us in that span. Beyond that boundary is more universe, potentially infinite, but we can't see it, and we never will because the light hasn't arrived yet, and due to the expansion of space, never will. This boundary, called the cosmic light horizon, is about 46 billion light-years away in all directions. It's not a wall or an edge. It's just the limit of what we can observe. There could be countless galaxies, stars, perhaps even civilizations out there beyond our horizon, forever invisible to us. It's both lonely and comforting. We are isolated by the speed of light and the expansion of space, but we're also complete within our own bubble of visibility. We have our own universe, vast and full, and it's enough. It's more than enough. You don't need to see everything to appreciate the beauty of what you can see. The concept of infinity appears often in cosmology. Is the universe infinite in size? We don't know. It could be, or it could be finite but unbounded like the surface of a sphere, no edge but not infinite either. Does time go on forever? Probably, though the far future is strange and hard to predict. Will the universe expand forever? Current evidence suggests yes. As dark energy drives galaxies apart, the universe will grow colder, emptier, darker. Stars will burn out, black holes will evaporate, and eventually, in a time frame so long it's almost meaningless, the cosmos will reach a state of maximum entropy, a heat death where nothing changes anymore. But that's trillions upon trillions of years away. For now, for the next hundreds of billions of years at least, there will be stars, galaxies, light, warmth. The universe is still young in that sense, still full of possibility. And even in the deep future, who knows? Perhaps new physics will emerge. Perhaps the universe will surprise us. It has before. Let your mind rest for a moment. You don't need to hold on to anything. Let the facts wash over you like waves lapping at the shore, each one arriving and then receding, leaving only a sense of calm. Your body is heavy and relaxed. The universe is large and you are small, and that's perfectly okay. In fact, it's wonderful. You are free from the weight of being important. You can simply be. Breathe in slowly. Breathe out even slower. There's nowhere you need to be. Nothing you need to do. Just this. Just now, just rest. Time dilation is one of the strangest predictions of relativity, and it's been confirmed countless times. Clocks at different altitudes tick at different rates because gravity warps time. The stronger the gravity, the slower time moves. This means that if you spend your life on a mountain, you'll age slightly faster than someone who lives at sea level because you're experiencing slightly weaker gravity. The difference is minuscule, nanoseconds over a lifetime, but it's real and measurable. GPS satellites have to account for time dilation. Their clocks run faster than clocks on Earth's surface because they're farther from the planet's gravitational pull. If engineers didn't correct for this, your GPS would quickly become inaccurate. Time is not the fixed, universal drumbeat we imagine. It's flexible, local, personal. Every clock tells its own story. Every observer has their own present. And in that flexibility, there's a strange kind of freedom. Time moves at the pace it needs to, shaped by motion and gravity, bending to accommodate the universe's deeper symmetries. Black holes warp spacetime so intensely that they create what's called an event horizon, a boundary beyond which nothing, not even light, can escape. Once you cross it, you're pulled inexorably toward the center, the singularity, a point where density becomes infinite and the laws of physics as we know them break down. But here's the interesting part. From your perspective, falling into a black hole might not feel violent. If the black hole is large enough, the tidal forces at the event horizon are gentle. You'd cross the boundary without noticing, still seeing the universe outside, though increasingly distorted. Time, from your perspective, would seem normal. But to an outside observer, time would slow for you as you approach the horizon, and you'd appear to freeze, never quite crossing, your image redshifted and dimmed until it faded away. You'd de-experience the fall, they'd never see it complete. Two realities, both true, both valid. The universe is full of such dualities, perspectives that seem contradictory but aren't. Reality is richer and stranger than any single viewpoint can capture. Wormholes are hypothetical tunnels through space-time, shortcuts that could, in theory, connect distant parts of the universe or even different times. Einstein's equations allow for them, but whether they actually exist or could ever be traversed is unknown. They require exotic matter with negative energy to hold them open, something we've never observed. Even if they exist, they might be microscopic, unstable, and utterly useless for travel. Still, they capture the imagination because they represent the ultimate cosmic shortcut. Step through a wormhole, and you might emerge on the other side of the galaxy, or even in another universe entirely. It's speculative, yes, almost certainly beyond our reach, but the fact that the math permits it, that the universe's rulebook doesn't outright forbid it, is tantalizing. The cosmos is more flexible, more open to possibilities than our everyday experience suggests. Even if we never find a wormhole, the idea itself is a gift, a reminder that reality is not fully explored, not fully understood, and still full of mysteries waiting at the edges of theory and imagination. The many worlds interpretation of quantum mechanics suggests that every time a quantum event has multiple possible outcomes, the universe splits into branches, each representing one outcome. In one branch, you made tea this morning. In another, you made coffee. In another, you skipped breakfast entirely. If this interpretation is correct, and it's just one interpretation, not proven, then there are countless parallel universes, an unimaginably vast multiverse where every possibility is realized somewhere. It's dizzying to think about, but also oddly comforting. Every choice you didn't make is made in some other branch. Every missed opportunity is seized elsewhere. You are living one path, but the you that might have been is living others. It takes the pressure off in a way. You don't have to be everything. You just have to be you here now in this branch of reality. And that's enough. You are enough. This universe, your universe, is enough. The concept of spacetime treats space and time as a single, interwoven fabric. You can't separate them, they're different dimensions of the same thing. Events don't happen in space and then in time. They happen in spacetime at specific coordinates along 4 dimensions. Moving through space means moving through time and vice versa. The faster you move through space, the slower you move through time, and the total speed through spacetime is always the same, the speed of light. It's as if the universe gives everyone the same amount of motion to spend, and you can allocate it between space and time however your velocity dictates. This is why nothing with mass can reach the speed of light. You'd be moving through space so fast that your motion through time would stop entirely. You'd be frozen in time, experiencing no passage of it at all. Light itself exists in this state, moving through space at maximum speed, experiencing no time. From a photon's perspective, emitted and absorbed in the same instant, the journey is instantaneous. Time and space are not what they seem. They're woven together in a tapestry we're only beginning to read. The anthropic principle suggests that the universe's properties are finely tuned to allow for the existence of observers like us. Change certain fundamental constants even slightly. The strength of gravity, the charge of the electron, the mass of the proton, and stars wouldn't form, or atoms wouldn't be stable, or chemistry as we know it couldn't exist. Some see this as evidence of design, others as a selection effect. We observe a universe that permits observers because we couldn't exist in any other kind. If there are countless universes with different properties, we naturally find ourselves in one that allows life. It's a profound question with no definitive answer, but it invites reflection. Whether by chance or necessity, the universe is astonishingly hospitable to complexity, to structure, to life. We are here because the cosmos made room for us. And tonight, as you rest, the universe continues to uphold the delicate balance that makes your existence possible. Gravity holding the planet together, atoms forming molecules, energy flowing in gentle rhythms. You are supported, held, made possible by the very structure of reality. The sound of the Big Bang, if you could have heard it, would have been a deep, resonant hum, the fundamental tone of the early universe. Scientists have analyzed the patterns in the cosmic microwave background and translated them into sound waves, a technique called sonification. What they found was a kind of cosmic chord, a mixture of frequencies corresponding to density variations in the primordial plasma. It's not a sound you could have heard with ears, of course. There was no air, no medium for sound waves in the usual sense. But the pressure waves in the hot plasma were real, and they left their imprint on the structure of the universe. In a sense, the galaxies and galaxy clusters we see today are echoes of that ancient sound, frozen into the architecture of space. The universe began with a chord, a vibration, and everything since has been a slow, grand elaboration on that original theme. It's music on the largest possible scale, and you are a note within it, a small but essential part of the symphony. The Higgs field is a quantum field that permeates all of space, and it's responsible for giving particles mass. Before the Higgs field was turned on in the early universe, particles had no mass. They zipped around at the speed of light. But as the universe cooled, the Higgs field settled into a non-zero value, and particles that interacted with it gained mass, slowing down. This was essential for the formation of atoms, chemistry, and eventually us. In 2012, scientists at CERN confirmed the existence of the Higgs boson, a ripple in the Higgs field, and it was a monumental discovery. It's strange to think that your mass, the weight you feel pressing into the mattress, comes from an invisible field filling all of space. You're not just sitting in the universe. You're interacting with it at a fundamental level, constantly, seamlessly. The Higgs field is holding you together, giving substance to the particles that make up your atoms. You are a collaboration between matter and fields, energy and structure, woven into the very fabric of reality. Entropy is a measure of disorder, and the second law of thermodynamics says that in any closed system, entropy always increases over time. This is why ice melts, why coffee cools, why things fall apart. The universe is moving from order to disorder, from structure to smoothness, from complexity to simplicity. And yet, here we are, complex, ordered, alive, existing in apparent defiance of that trend. How? Because the universe isn't a closed system locally. Energy flows from the sun, driving processes on Earth, allowing life to build and maintain complexity. We are islands of low entropy in a sea of increasing disorder, sustained by the energy streaming down from a star. It won't last forever. Eventually, the sun will die, the stars will burn out, and the universe will reach maximum entropy. But that's unimaginably far away. For now, Entropy's slow march gives structure to time, gives meaning to change, and allows you to be here, warm and alive, a temporary, beautiful eddy in the flow of cosmic disorder. You're not fighting the universe. You're part of its natural unfolding, a brief, brilliant flourish in the long drift toward stillness. The speed of dark, the speed at which darkness moves, is, oddly enough, the same as the speed of light. When you turn off a lamp, darkness doesn't rush in. The light simply stops arriving, and darkness is what remains. Darkness is the absence of light, so it moves at whatever speed light stops reaching a place. It's a playful concept, but it reminds us that darkness is not a thing in itself. It's just the baseline, the natural state of space. Light is the visitor, the active presence. And yet, we fear the dark and seek the light. Tonight in the dark, you're safe. The darkness is not an enemy. It's simply the canvas on which light is painted, the quiet background against which stars shine. Without darkness, there would be no stars. Without silence, no music. Without rest, no waking. Opposites define each other, and both are necessary. So let the darkness cradle you. It's not empty. It's full of potential, of peace, of the promise that morning will come again. Quantum entanglement is one of the most mysterious phenomena in physics. When two particles become entangled, their properties become linked in such a way that measuring one instantly affects the other, no matter how far apart they are. It's not that information is traveling between them faster than light. Nothing is being sent. It's more that the two particles share a single quantum state, and observing one collapses that state for both. Einstein famously called it spooky action at a distance, and he was uncomfortable with it, but experiments have confirmed it again and again. Entanglement doesn't allow faster-than-light communication, so it doesn't violate relativity, but it does reveal something profound. The universe is deeply interconnected at the quantum level. Particles that were once together remain linked, no matter how far they drift apart. In a sense, nothing is truly separate. Everything that has ever interacted remains, in some subtle way, connected. You are entangled with the universe, woven into its quantum fabric, part of a whole that transcends space and time. The cosmological constant, also known as dark energy, is sometimes thought of as the energy of empty space itself, a kind of baseline tension woven into the fabric of the vacuum. Even in the emptiest regions of space, where there are no particles, no radiation, nothing at all, there's still this energy pushing space to expand. It's incredibly weak, so weak that it only becomes noticeable on cosmic scales, but it's persistent, never fading, never changing. Over time, it dominates the universe's evolution. Why does empty space have energy? We don't know. It's one of the deepest mysteries in physics. Some have speculated it's related to quantum fluctuations, the constant bubbling of virtual particles popping in and out of existence. Others think it's something else entirely. But whatever it is, it's gentle, patient, and utterly pervasive. The universe is not passive or inert. Even its emptiness is alive in a sense, humming with a quiet, unseen energy, pushing the galaxies apart, shaping the destiny of everything. You are floating in an ocean of subtle forces, all of them working together to create the cosmos as it is. The first stars in the universe were unlike any stars we see today. They formed from clouds of primordial gas made only of hydrogen and helium. No heavier elements existed yet. These stars, called population III stars, were likely enormous, hundreds of times the mass of the Sun, burning furiously and dying quickly in spectacular supernovae. Those explosions scattered the first heavy elements into space, seeding the next generation of stars with the raw materials for planets, and, eventually, life. We've never observed a population III star directly. They all died billions of years ago, but we see their legacy everywhere. Every atom in your body heavier than helium was created inside a star or a supernova. You are made from the ashes of those ancient giants, the first stars that lit up the cosmos after the Dark Ages. There's a lineage to your atoms, a history stretching back to the very beginning, and it connects you to the deepest past of the universe. You are not separate from the cosmos. You are its continuation, its expression, its way of knowing itself. The Great Attractor is a massive gravitational anomaly located about 150 million light-years away, in the direction of the constellations Hydra and Centaurus. It's pulling our galaxy, along with hundreds of thousands of others, toward it at a speed of about 1.4 million miles per hour. We can't see it directly because it lies behind the crowded plain of the Milky Way, obscured by dust and stars, but we can detect its influence. Later observations revealed that the Great Attractor is itself part of an even larger structure called the Laniakea supercluster, a vast web of galaxies spanning 520 million light-years. We are moving through space, not randomly, but along paths defined by gravity and the large-scale structure of the universe. It's a cosmic current, a flow we're part of, and we're drifting together with countless other galaxies toward some distant center of mass. There's something humbling and comforting about that. We're not alone. We're part of a crowd, all moving together, all pulled by the same invisible force, all part of the same grand structure. The coldest place in the universe, as far as we know, is not in deep space but here on Earth, in laboratories where scientists use lasers and magnetic fields to cool atoms to within a fraction of a degree above absolute zero. At absolute zero, minus 273.15 degrees Celsius, all atomic motion would stop. It's the ultimate cold, the lowest possible temperature, and the laws of thermodynamics say you can never quite reach it. You can only get closer and closer. In space, the cosmic microwave background keeps the baseline temperature at about 2.7 Kelvin, so even the emptiest voids are not truly at absolute zero. But in labs, by isolating atoms and slowing them down, scientists have created temperatures colder than anywhere else in the cosmos. At those temperatures, quantum effects become visible at the macroscopic scale. Atoms behave in strange, collective ways, forming Bose-Einstein condensates, states of matter that don't exist at normal temperatures. The coldest cold reveals a hidden side of reality, a realm where quantum mechanics reigns and the familiar rules blur. The universe rewards those who look closely, who push boundaries, who explore the extremes. The hottest temperature ever achieved by humans occurred in particle accelerators like the Large Hadron Collider, where protons are smashed together at nearly the speed of light. These collisions, for a fraction of a second, create temperatures over 5 trillion degrees Celsius, far hotter than the center of the sun, hotter than any natural process in the universe today. At those temperatures, matter breaks down into a quark-gluon plasma, a state that hasn't existed since microseconds after the Big Bang. Scientists study this to understand the early universe, to see what matter was like before atoms, before protons and neutrons, when everything was a hot, dense soup of fundamental particles. It's astonishing that we can recreate, in a small space for an instant, conditions from the birth of the cosmos. We are reaching back in time, using machines and ingenuity to touch the origin of everything. And in doing so, we're learning not just about the past, but about the fundamental nature of matter, energy, and the forces that bind the universe together. The universe is filled with light, not just from stars, but from the collective glow of all the stars that have ever existed. This is called the extragalactic background light, and it's a faint but measurable sea of photons stretching across all wavelengths, from radio to gamma rays. Most of it is in the infrared, the accumulated light from stars and galaxies across billions of years, redshifted and dimmed by the expansion of space. When you look at a dark patch of sky, it's not truly empty or dark. It's filled with faint, ancient light from countless sources, too dim for your eyes to see, but they're nonetheless. The universe is glowing softly everywhere. There's no true darkness, just varying shades of faint luminosity, and that's oddly comforting. Even in the vast emptiness, there's light, there's warmth, there's evidence of stars that shone and lives that were lived. The universe remembers. It holds onto the light, carrying it forward, letting it fade slowly but never vanish completely. The Fermi paradox asks a simple question. If the universe is so vast and so old, why haven't we encountered any other intelligent civilizations? There are billions of stars in the Milky Way, many with planets, and the galaxy is billions of years old. Plenty of time for life to arise, evolve, and spread. And yet we see no signs of alien technology, no megastructures, no radio signals, no visitors. Why? There are many possible answers. Maybe intelligent life is incredibly rare. Maybe civilizations destroy themselves before they can spread. Maybe they're out there but not interested in contacting us, or using communication methods we don't recognize. Maybe the distances are just too vast, and interstellar travel or communication is harder than we think. Or maybe we're simply the first, the earliest intelligence in the galaxy, and the universe is waiting for us. The Fermi paradox is unsettling and profound, but it's also open-ended. We don't know the answer, and until we do, we're left to wonder, to search, and to contemplate our place in a cosmos that might be teeming with life or might be, for now, astonishingly quiet. Take a moment to notice how you feel. Your breathing is slow, your body is still. The facts are drifting past you like clouds or stars, and you don't need to catch them. Let them go. The universe is patient. It doesn't demand anything of you. Right now, you're exactly where you need to be, here, resting, letting go of the day. There's no test. There's no urgency. Just the gentle rhythm of your breath and the quiet knowledge that the cosmos is vast and you are safe within it. Let yourself sink deeper. You're doing beautifully. Voyager 1, launched in 1977, is the farthest human-made object from Earth, currently over 14 billion miles away in interstellar space. It's traveling at about 38,000 miles per hour, carrying a golden record with sounds and images from Earth. a message in a bottle for anyone or anything that might find it in the distant future. It's still sending back data, though the signal is faint and the power is running low. In a few years it will go silent, and it will drift through space for millions, perhaps billions of years, an artifact of a civilization that briefly looked outward and wondered. Voyager is a testament to human curiosity, to the impulse to explore, to reach beyond our small world. And it's also a reminder of scale. After 45 years of travel, it has barely left the sun's neighborhood. The nearest star is still tens of thousands of years away at Voyager's speed. Space is vast beyond imagining, and we are small, but we tried. We sent a piece of ourselves into the cosmos, and it's out there now, alone but not forgotten. The concept of a multiverse suggests that our universe might be just one of many, perhaps infinitely many, each with different properties, different laws of physics, different histories. This idea arises from several areas of physics: quantum mechanics, string theory, cosmological inflation. If inflation, the rapid expansion of the early universe, is correct, then it might never truly stop, creating bubble universes endlessly, each one a separate cosmos with its own characteristics. We could never visit these other universes, or even detect them, but they might exist nonetheless, an infinite ensemble of realities, each one complete and self-contained. It's speculative, perhaps unprovable, but it expands the imagination. If the multiverse is real, then everything that can happen does happen somewhere. Every possibility is realized. And this universe, your universe, is just one thread in an unimaginably vast tapestry. It doesn't diminish your reality, it enriches it. You're part of something even bigger than we thought, something so large that large loses meaning. In about 4 billion years, the Milky Way and Andromeda galaxies will collide. But collide is misleading. They'll pass through each other, their stars so widely spaced that individual collisions will be extremely rare. Instead, gravity will pull the galaxies into complex shapes, long tidal tails, bridges of stars, chaotic swirls. Over hundreds of millions of years they'll merge, forming a single giant elliptical galaxy. The night sky, if anyone is around to see it, will be spectacular. A blaze of stars in motion, new star-forming regions ignited by the collision's shockwaves. Earth, if it still exists, might be flung into a different orbit, or even ejected from the galaxy entirely. But by then the sun will be nearing the end of its life, and Earth's fate will already be sealed. Still, the collision is a reminder that even galaxies are not eternal. They change, merge, evolve. The universe is dynamic, always moving, always transforming. Nothing is static, nothing is forever. And yet, for now, the Milky Way is stable, calm, and home. The Hubble Space Telescope, launched in 1990, has given us some of the most iconic images of the cosmos. One of the most famous is the Hubble Deep Field, a photograph of a tiny patch of seemingly empty sky, no bigger than a grain of sand held at arm's length. Hubble stared at that patch for 10 days, collecting light, and when the image was processed, it revealed not emptiness but thousands of galaxies, each one a swirl of stars, stretching back billions of years in time. Everywhere we look, no matter how dark or empty the sky seems, there are galaxies. The universe is full. It's almost overwhelming. So many worlds, so many stars, so much history packed into every tiny sliver of the night. And yet it's also calming. We're not alone in space. The cosmos is crowded with structure, with beauty, with light. The universe is not a barren void. It's rich, textured, and astonishingly full of life, or at least full of the conditions for life. The concept of cosmic time allows us to talk about the universe's age and evolution as a whole. Even though time is relative and flows differently depending on your motion and position in a gravitational field, the universe has a kind of universal clock, the time experienced by observers who are at rest relative to the cosmic microwave background. These observers see the universe expanding uniformly around them, and for them, the universe is 13.8 billion years old. This cosmic time gives structure to cosmology, allowing us to say when stars formed, when galaxies assembled, when life might have begun. It's not that time is the same everywhere. Locally, it still bends and stretches. But on the largest scales, there's a shared history, a collective narrative. The universe has a story, and we're part of its current chapter. Tonight, as you rest, the story continues to unfold, slowly, patiently, across trillions of stars and countless worlds. SETI, the search for extraterrestrial intelligence, involves scanning the skies for signals that might indicate the presence of alien civilizations. For decades, radio telescopes have listened, searching for patterns in the cosmic noise, pulses, repeating sequences, anything that might be artificial. So far, we've heard nothing definitive. There have been intriguing signals like the famous "wow" signal detected in 1977, but none have repeated or been confirmed. The search continues, though, because the payoff would be profound. Discovering that we're not alone would fundamentally change our understanding of life, intelligence, and our place in the cosmos. But even if we never find anyone, the search itself is valuable. It reminds us to look outward, to wonder, to hope. And in the silence, there's a kind of peace. Maybe we're alone, or maybe we're just early, or maybe they're out there and we haven't listened in the right way yet. Either way, the universe is patient, and so are we. Magnetars are a type of neutron star with magnetic fields a quadrillion times stronger than Earth's. They're the most magnetic objects known in the universe, and their fields are so intense that they warp the very atoms around them. Occasionally, magnetars have starquakes, sudden shifts in their crust, that release enormous bursts of energy, including X-rays and gamma rays. One such burst, detected in 2004 from a magnetar 50,000 light-years away, was so powerful that it briefly ionized Earth's upper atmosphere. If a magnetar existed within a few hundred miles of you, the magnetic field would be lethal, pulling at the iron in your blood, disrupting the electrical signals in your nerves. But magnetars are rare and distant, isolated remnants of massive stars, spinning alone in the dark. They're extreme, yes, but also contained, bound by the same laws that govern everything else. The universe has room for extremes, but it also has room for calm, for places like here, where magnetic fields are gentle and life can flourish quietly. Pulsars, those rapidly spinning neutron stars, were first discovered in 1967 by Jocelyn Bell Burnell, who noticed strange, regular pulses of radio waves coming from space. At first, the signals were so precise that the team half-joked they might be from aliens, and they nicknamed the source LGM-1, for Little Green Men. But further observation showed it was natural, a neutron star spinning rapidly, its magnetic poles beaming radio waves into space like a lighthouse. The discovery of pulsars was revolutionary. It confirmed that neutron stars existed, and it gave astronomers a new tool for studying the universe. Pulsars act as cosmic clocks, their pulses so regular that they rival atomic clocks on Earth. Some pulsars are part of binary systems, orbiting other stars or even other neutron stars, and by watching their pulses, scientists can study gravity, test relativity, and even detect gravitational waves. The universe is full of natural laboratories, places where extreme physics plays out, teaching us about the fundamental rules of reality. The Oort cloud, that vast, distant shell of icy bodies surrounding the solar system, might contain trillions of objects, each one a potential comet. It's so far away that sunlight there is incredibly faint, and temperatures hover just above absolute zero. Objects in the Oort cloud take millions of years to complete a single orbit around the sun. They drift in the dark, barely moving, frozen and silent. Occasionally, a passing star or gravitational perturbation nudges one of them inward, and it begins the long fall toward the sun, eventually becoming a comet we see from Earth. But most will never make that journey. They'll remain in the Oort cloud forever, part of the solar system but untouched, unseen, unfathomably distant. There's something peaceful about that. Objects existing quietly, far from light and warmth, content in their cold orbits, part of the family but distant relatives, remembered only when one makes the rare journey home. The surface of Mars is covered in iron oxide, rust, which gives it its characteristic red color. The planet is dry now, but there's evidence it once had rivers, lakes, perhaps even an ocean. Water flowed across its surface, carving channels and valleys that we can still see today. Where did the water go? Some is locked in ice at the poles. Some seeped underground. And much of it was lost to space, stripped away by solar wind after Mars lost its magnetic field. Mars is a ghost of what it might have been, a world that almost made it, that came close to remaining wet and warm but couldn't sustain it. And yet, we're drawn to it. It's the most Earth-like planet in the solar system, and the possibility remains that life once existed there, perhaps underground, perhaps in ancient lakes. Mars is a question mark, a world that invites exploration, and in our curiosity about it, there's hope, not just for finding life, but for understanding our own planet better, for learning what makes a world thrive and what makes it fade. The speed at which the universe is expanding is described by the Hubble constant, a number that tells us how fast distant galaxies are receding. Currently, it's about 70 kilometers per second per megaparsec, which means that for every 3.26 million light-years of distance, galaxies are moving apart at an additional 70 km/s. Measuring this constant has been a major goal of cosmology, and recent measurements have revealed a puzzle. Different methods give slightly different values. It's called the Hubble tension, and it might mean there's something we don't understand about dark energy or the early universe or the expansion itself. Or it might just be a measurement issue that will resolve with better data. Either way, the universe is not done teaching us. Even our most fundamental observations still hold mysteries. The cosmos is vast, and our understanding, while impressive, is incomplete. And that's okay. There's always more to learn, always another layer to uncover. The journey of discovery is endless, and that's part of what makes it beautiful. In the future, stars will become rarer. Star formation requires gas, and over time, galaxies are using up their gas, turning it into stars. In a few trillion years, the last stars will form, and after that, no more will come. Existing stars will burn out, one by one, and the universe will grow darker. Red dwarfs will be the last to go, smoldering for trillions of years before finally fading. And then there will be only remnants, white dwarfs, neutron stars, black holes, slowly cooling, slowly evaporating. The universe will enter what's called the degenerate era, a time when the sky is dark and cold, when galaxies are just scattered embers drifting through space. It sounds bleak, but it's also unimaginably far in the future. For now, the universe is bright. Stars are still being born. Galaxies are still full of light. And you are here alive in the universe's youth, witnessing its beauty. You're lucky, really, to exist in this era when the cosmos is still vibrant, still full of possibility, still singing its slow, luminous song. The concept of a theory of everything is the dream of physicists. A single framework that would unify all the forces of nature and explain everything from the smallest particles to the largest structures. Currently, we have two great theories: general relativity, which describes gravity and the large-scale structure of spacetime, and quantum mechanics, which describes the behavior of particles at the smallest scales. Both work incredibly well in their domains, but they're incompatible with each other. At the edges, like inside black holes or at the moment of the Big Bang, they both break down. A theory of everything would reconcile them, perhaps through string theory, loop quantum gravity, or some other framework we haven't discovered yet. It's the holy grail of physics, and we're not there yet. But the search itself has taught us so much, deepened our understanding, and revealed new mysteries. And maybe that's the point. Maybe the universe doesn't want to be fully known. Maybe it wants to keep some secrets, to always offer one more question, one more puzzle. And maybe that's perfect. A universe fully understood might be less wondrous. Mystery, in its own way, is a gift. Hawking radiation is a theoretical prediction that black holes are not entirely black. They actually emit a faint radiation due to quantum effects near the event horizon. This radiation is incredibly weak, far too faint to detect from any real black hole, but over an unimaginably long time, it would cause the black hole to slowly evaporate. A stellar mass black hole would take longer than the current age of the universe many times over to evaporate, and supermassive black holes would take even longer, 10 to the 100th power years, numbers so large they're almost meaningless. But eventually, even black holes die. Nothing is permanent. Not stars, not galaxies, not even the ultimate sinks of gravity. The universe will outlast everything, moving slowly toward maximum entropy, toward a state of uniform cold stillness. But that's okay. Endings are part of the cycle. And in the meantime, right now, there's warmth, light, structure, and you. You're part of the universe's story during its most interesting chapter, and that's something to appreciate, even as you drift off to sleep. The Planck length is the smallest meaningful length in physics, about 1.6 x 10^35 meters. Below that scale, the very concept of distance breaks down, and quantum fluctuations in spacetime become so intense that the smooth fabric of space we're familiar with no longer exists. Similarly, the Planck time, about 5.4 x 10^44 seconds, is the smallest meaningful unit of time. These scales set the limits of our current understanding. We can't probe smaller distances or shorter times with any known physics. It's possible that at the Planck scale, space and time are not continuous but discrete, made of tiny, indivisible units, quanta of spacetime itself. The universe might be pixelated at the deepest level, like a cosmic screen made of unimaginably tiny dots. Or it might be something else entirely, something we don't have the language or math to describe yet. These limits remind us that there are boundaries to knowledge, edges where our theories run out. And standing at those edges, looking into the unknown, is both humbling and exhilarating. The universe still has depths we can't fathom. Vacuum fluctuations are a strange consequence of quantum mechanics. Even in completely empty space, with no particles, no energy, nothing at all, the quantum fields that fill space are never truly still. They fluctuate, creating pairs of virtual particles that pop into existence, and then annihilate each other almost instantly. These fluctuations are real, they've been measured, and they have observable effects like the Casimir effect, where two metal plates placed close together in a vacuum experience a tiny attractive force due to the virtual particles between them. The vacuum is not empty. It's a seething sea of potential, of temporary particles and fields, a background hum of quantum activity. Even nothingness is something. Even emptiness is full. It's a reminder that the universe is deeply, fundamentally active, even at rest. There's no such thing as true stillness, true emptiness. Everything is in motion always on every scale, and you're part of that motion, that activity, that endless unfolding. The Drake equation is a formula that estimates the number of active, communicative extraterrestrial civilizations in the Milky Way. It multiplies factors like the rate of star formation, the fraction of stars with planets, the number of planets that could support life, and so on. The problem is, most of these factors are highly uncertain. We can guess, but we don't really know. Depending on the values you plug in, the equation can suggest thousands of civilizations in the galaxy or only one us. It's less a predictive tool and more a way of framing the question, of identifying what we need to learn. And in that sense, it's valuable. It tells us what to look for: habitable planets, biosignatures, technosignatures. It gives us a roadmap for the search. And even if we never find anyone, the search changes us. It makes us think about life, intelligence, and our responsibilities as possibly the only conscious beings in a vast, quiet galaxy. It's a sobering thought, but also an empowering one. If we're alone, then the future of intelligence in this part of the universe is up to us. Time might have had a beginning, but will it have an end? Current cosmology suggests that time will continue indefinitely. The universe will keep expanding, stars will burn out, black holes will evaporate, and entropy will increase until everything reaches a state of maximum disorder, a heat death where nothing changes anymore. But even then, time would still pass, wouldn't it? Or would it? If nothing changes, is there any meaningful difference between one moment and the next? Time is defined by change, by the sequence of events. Without events, without change, does time even exist? It's a philosophical question as much as a scientific one. The far future of the universe is strange and uncertain, and our intuitions about time break down. But that's trillions upon trillions of years away. For now, time flows, change happens, and the universe is full of activity. Your life, brief as it is on cosmic scales, is a moment of vibrant change, of complexity and consciousness. You're here now, and that's what matters. The universe is experiencing itself through you, and tonight it's resting. Let yourself rest too. Let everything soften now. Your mind doesn't need to follow every word anymore. You can let them blur together, a gentle murmur of cosmic wonder. The universe is vast and it's holding you. You're safe. You're warm. There's nothing to solve, nothing to remember, just the soft rise and fall of your breath. Feel the stillness. Feel the quiet. You're drifting, and that's exactly what you should be doing. There's no rush, no destination, just this gentle, peaceful floating. Let go. And so, we've wandered together through the vastness of the cosmos, past stars being born and dying, through galaxies colliding and merging, across distances so large that light itself takes billions of years to cross them. We've touched on black holes and dark energy, on the cosmic microwave background and the possibility of other worlds, other lives. We've explored the architecture of space and time, the quantum strangeness at the heart of matter, and the patient, inevitable unfolding of entropy. But what does it all mean for you here now in this moment? Maybe it means that your worries are smaller than you thought, not unimportant, never unimportant, but placed in a context so vast that they lose some of their weight. The universe has been here for 13.8 billion years. It will be here for trillions more. And in all that time and all that space, there is only one you, only one now. You are unique. You are brief. And that makes you precious. You are the universe waking up to itself, a fleeting moment of consciousness and wonder in an ocean of time. That's not insignificant. That's profound. Maybe it means that you're connected to everything. The atoms in your body were forged in stars, scattered by supernovae, gathered into clouds, and eventually into you. You are made of the cosmos. You are not separate from it. You are part of it deeply, fundamentally. When you breathe, you're cycling atoms that have been through countless other beings, other places. You're part of the great exchange, the endless recycling of matter and energy that has been going on since the beginning. You are the universe, localized, experiencing itself from your unique perspective. Maybe it means that it's okay to rest. The universe operates on timescales that dwarf human lifetimes. Stars burn for billions of years. Galaxies drift for eons. There is no rush. The cosmos is patient, and it teaches patience. You don't have to do everything today. You don't have to solve everything tonight. You can let go. You can close your eyes. The universe will still be here tomorrow, still unfolding its mysteries, still inviting you to wonder. And when you wake, you'll be part of it again, renewed, ready to take your small, beautiful place in the grand tapestry. I'm so glad you joined me tonight. Whether you're still awake or already drifting into sleep, I hope you found something here. A sense of scale, a moment of calm, a reminder that you're part of something infinitely larger and infinitely beautiful. The cosmic universe is vast, yes, but it's also gentle. It holds you. It made you. It welcomes you home every night when you close your eyes. If you enjoyed this journey, consider subscribing so you can take more of these trips with me. There are so many more topics to explore, so many more gentle facts to fall asleep to, but there's no pressure. You're here now, and that's enough. Sleep well. Dream of distant stars, of quiet nebulae, of the slow, patient spin of galaxies. Let the cosmos cradle you, Let the darkness be a comfort, and let yourself drift into the deep, peaceful rest you deserve. Good night. The universe loves you, and so do I.